Welcome everyone. This is sixth video in graph theory series. In this video, I am going to talk about the following topics: planar graph, Euler's formula, which is very important, and its related corollaries, homeomorphic graph, Kuratowski's theorem, Peterson graph, and crossing number and thickness of a graph. So let's start. But before I start, I would request you that in case if you are new to the channel, you should subscribe it. So ladies and gentlemen, if you look at this graph, we are going to draw its planar representation. But before that, let us look at the definition. A graph is called planar if it can be drawn in the plane without any edge crossing. It means what? It means, understand it through this example. And such a drawing is called planar representation of the graph. So what is the drawing here? Suppose we have four vertices, right? And we want to join the edges in such a way that no edge cross each other. So till this time, no edge is crossing each other. I can draw this like edge also. So here also there is no crossing happening. The crossing is happening at this point if I draw this edge like the way it has been drawn. But this crossing can be avoided. How it can be avoided? We can join these two vertices like this. Now you can see that everything is same except the situation that we came across here, that here these two edges are crossing, but here that crossing has been avoided by redrawing this edge. Now this representation of this graph is known as planar representation. Basically, I hope you all remember that this graph is K4, that is complete graph with four vertices. So this is a planar representation of K4 graph. Now if you look at this graph, I hope you all remember that this is 3 cube graph or Q3, and if I have to draw its planar representation, I can draw it. But before I draw it, let us quickly name the vertices for our convenience. Suppose I call this vertex, vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, 7 and 8. So to draw its planar representation, first I am going to draw this four vertices, 1, 2, 3, 4. So I just have drawn these vertices, and let us join them like the way they are joined as the surface here, because you can see this is the surface, bottom surface of the cube, and number it as 1, 2, 3, and this vertex is vertex 4. Now to draw the planar representation, what I am going to do, I am going to draw another square kind of a structure here, and just going to look at the way the vertices are adjacent to each other. So if you look at this vertex, the vertex 2 is adjacent to 1 and 3, and it is adjacent to 6. So what we can do, we can call this vertex 6 and join this. So that will take care of the requirement for 2. Now if I talk about the vertex 1, it is adjacent to 2 and 4, which we already have joined, and I just need to connect it with the vertex 7. So let us call this vertex 7 and connect this to 1. Now what about 3? So 3 is adjacent to 2 and 4, which I already have joined here. 3 is adjacent to 2 and 4, and it is also adjacent to this vertex 5. So I am going to join this vertex 5 here. And finally, if you look at the vertex 4, where is it? It is 4 here, which is adjacent to 1. So here also it is adjacent to 1 and 3. Only thing is that we need to join it to 8. So I'm going to join it to 8, and this vertex I'm going to call. Now if you look at this new graph that I have drawn is not a new graph basically. This is just a planar representation of Q3 graph. Okay. So to draw the planar representation, only thing that we need to be careful about, that when we are drawing it, none of the edges should cross each other. Okay, so let us now talk about this graph that is popularly known as complete bipartite graph, K33, and this is a very important graph that we will be talking about why it is important. But for the time being, let us try to draw its planar representation. Whether I will be able to draw it or not, that is a different method, but first let us try. So these vertices are V1, V2 and V3, and we have V4, we have V5, and we have V6 here. So V1 is joined to all the three vertices. So without thinking much, quickly join them to all the three vertices on the other side. I hope this is how the bipartite graph, complete bipartite graph look. Now if I talk about V3, so V3 can be joined to V6, V2 can also be joined to V6, because I am drawing those edges where the crossing is not happening. Now the degree of V1 is 3 and the degree of V6 is also 3, because here each of the vertex will have degree 3, so that will help me to take an keep an eye on that whether we are missing an edge or not. So now we are already done with V1 and V3, sorry, V1 and V6. Now let us come to the vertex V3. So you can clearly see that this V5 can be joined to V3 in this way. So I am joining V5 to V3. To avoid the crossing, I have gone like this. And we can also join V5 to V2, and to join V5 to V2, what we can do? There are many ways, but let us join V5 to V2. So another the way to join V5 to V2 is that I avoid this crossing and I am joining it to V2. Okay. Now degree of this vertex is 3, degree of this vertex is 1, 2, 3, so I am also done with this. Okay. Now how can this this degree is 1, so I need to join it to V2 and V3. Yes. So can it be done? So to join it to V2, I can draw it like this. So see, I have joined it to V2. Now the degree of this vertex is also 3. So 3, 3, 3, 3. Now this vertex is of degree 2 and this vertex is of degree 2. Means I need to join this vertex and this vertex. And I want to avoid any crossing. So now the question is, take a pause, and can you avoid the crossing? You can't avoid the crossing, but you can certainly minimize the crossing. So what is the minimum number of crossing that will happen if I join these two vertices? So the minimum number of crossing that will happen, and let me use a different color so that we don't miss the point. So I want to join this vertex and this vertex. So what we can do, let us start here, go from this direction. We are not touching any, and then I am going and joining it to this. Now did you notice that we are having one crossing here at this point? So it is not possible basically to draw K33 without avoiding any crossing. And I would suggest you that this is not the only way to draw the graph so that we can avoid the crossing. There are other ways also. If I draw it some other time, possibly I will draw it in some other way. Only thing that I am trying to do is that I am trying to avoid the crossing, and to avoiding up to such an extent that it can be minimized. But in the end we noticed that one crossing is inevitable, means it will certainly happen. One crossing, no matter how much you try, you can't avoid this one crossing, right? So since it is not possible to draw K33, so K33 is not a planar graph, not a planar graph. Yes, ladies and gentlemen, I hope you are getting. So the first two examples that I took was example of planar graph, because I could draw the planar representation, but K33 could not be drawn. So this is not a planar graph. Now let us talk about the next thing. So the next thing that I'm going to talk about is Euler's formula. And before I talk about Euler's formula, I would suggest you to pause the video and try to draw the planar representation of K5. I think I need to draw the planar representation of K5 also, because K5 is a very important graph, even though it will make the video slightly longer. But since we need to discuss everything, so let us talk about K5. So you know that this is how the K5 looks like. So there are 5 vertices. Let me call it V1, V2, V3, V4 and V5. And first draw the way we already have drawn in our previous classes, that without avoiding the crossing, just draw it. So is it K5? I am done. The degree is 4 here, the degree is 4 here, degree is 4, degree is 4 and degree is 4. And now let us try to draw its planar representation. So we have 5 vertices, 1, 2, 3, 4, 5. And first we can join these 5 edges, and I think it is very much clear that here no crossing will happen. So let us call it V1, V2, V3, V4 and V5. Now I can join V2 and V5. I can join this, right? Now the degree of this vertex is 4, so I am done with this. Now degree of this vertex is 3, 1, 2, 3, and I need to join it with V1. But since I want to avoid the crossing, I can move like this. So I moved like this. I avoided the crossing and I joined V1 and V4. So now degree of 1, 2, 3, 4, V4 became 4. Now V1 has degree 3, so it is joined to V4, it is joined to V2, it is joined to V5. It is not joined to V3, right? So what we need to do, we need to join it to V3. So I can join it to the V3 like this. Now this crossing has been avoided. Till now there is no crossing. Now degree of this also became 4. So we have 3 vertices of 4 degree and we have 2 vertices left with degree 3. So I need to join V5 and V3. Now the question is, can you avoid the crossing? The answer is no, you can't. So if I join them, I can join it like this. So this crossing is happening, right? This crossing is happening. So that is why the K5 graph, K5 is also not planar. And I have actually drawn K5 and K33 both because these two are very important graphs which I am going to look at in the coming videos, or maybe in this video in the latter part, right? So let us move to the next thing, Euler's formula. And it is one of the most important result in graph theory. So be clear about this. So what this formula tells you, that let G be a connected planar simple graph. Connected planar and simple graph. Planar means, first of all, you need to be sure that whether the given graph has a planar representation or not. If the graph is not planar, we can't apply the Euler's formula. So to apply the Euler's formula, the graph should be connected, planar and simple. And I hope you are clear about these terms, because in the previous videos I have talked about what is connected graph, what is planar graph, what is simple graph. And if E is the number of edges, V is the number of vertices, and let R be the number of regions in a planar representation of the G, then R is equal to E minus V plus 2. This is how it is written, but you know, I personally prefer to write this result. Let me write. I will write is this as V minus E plus R is equal to 2. This is my personal preference, right? So I remember this like this. I hope you are smart enough to realize that these two are not different result. These two are the same result, because here I have taken everything in the left hand side. So minus B becomes plus V, E becomes minus E and plus R. So V minus E plus R is equal to 2. But one thing you might be thinking that, sir, I know what is the number of vertices in a graph, what is the number of edges in a graph, but I don't know the reason. So basically, what is the reason of a graph? So to understand this, let us go to the previous page, and if I ask you to count the number of regions in the graph, so this is the first reason. Reason is like, this is one of the regions of the graph, this is another region of the graph, this is the third region of the graph, and there is a region which is lying outside also, so that is the fourth region, right? We don't miss to count the region lying outside also. So if I talk about this particular graph, you can clearly see that it has 1 region, 2 region, 3 region, 4 region, 5 region, and there is 1 region outside this also, so that is the 6th region. So I hope you got the point that how to count the region. So in this given graph, how many vertices are there? In this graph, 1, 2, 3, 4, 5, 6, 7 vertices are there. So number of vertices V is equal to 7, right? How many edges are there? So let us count it. So number of edges are, let us count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 edges, and we already have counted the number of region, that is R is equal to 6. Region, I hope you understand, the bounded area, like R1 is 1, R2 is 2, R3 is 3, R4, so that we already have counted 6 region. Now this result tells me that the formula V minus E plus R should be what? So V is 7, E minus E is 11, R is 6. So we got 13 minus 11 is equal to 2. So this is how the Euler formula look like. It will work for any planar graph. In case if you want to see some more example, let us go back to the previous page and verify that whether it is true for this or not. So if I want to verify the Euler's formula for this, let me change the color so that we don't get confused. So ladies and gentlemen, to apply the Euler's formula, first of all, we need to look at its planar representation. So how many vertices are there? If I talk about this graph, the number of vertices V is equal to 4. How many edges are there? Number of edges is equal to 6. You can count them. 1, 2, 3, 4, 5, 6. So 6 edges are there. And how many regions are there? So this is one region, region 1, region 2, region 3, and region 4. We already counted. So R is equal to 4. So what is V minus E plus R? So V is equal to 4, minus E 6, and R 4. So that is equal to 2. So this is true for the planar representation. If I verify for this, how many vertices are there? Can I write it over here? The number of vertices are 8. How many edges are there? We know that there are 12 edges. I hope when you attended the previous lecture or maybe the previous video, you might be aware. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And how many regions are there? So region 1, region 2, region 3, region 4, region 5, region 6. So 1 and then 4 and 1, 5, 6. So regions are 6. So you can clearly see that V minus E means 8 minus 12 plus 6 is equal to 2. So this result is true for any planar representation of a graph. Okay. I hope the presentation is not looking very clumsy, but to explain the things, I think I need to do it. So ladies and gentlemen, let us quickly solve this problem. Suppose that a connected planar simple graph, so connected planar simple means we can apply the Euler's formula, has 20 vertices. So the number of vertices is equal to 20. Each vertex is of degree 3. So how many regions does a representation of this planar graph split the plane? So first of all, to apply the Euler's formula, V minus E plus R is equal to 2, I need to know what is V, what is E, and since they are asking R, so that we can calculate. So how to count the number of edges? So there are 20 vertices and each vertex is of degree 3. So what is the sum of the degree of the vertices? 20 into 3. And we know from the handshaking theorem that this is twice the number of edges. So it means what? That the number of edges is 20 into 3 by 2 is equal to 30. I hope you remember the handshaking theorem. Now V minus E plus R. So V is, what is V? So V is 20 minus 30 and R that I have to calculate is equal to 2. So what is the value of R? The value of R is 2 plus 10 is equal to 12. So the planar representation of the graph will split the plane into 12 regions. Okay, I hope it is clear. Now these three are very important result, and lot of questions are asked in competitive exam related to this. So there are three corollaries, and I'm going to state them, and I would request you to try to prove the corollary, right? So what is the first one? If G is a connected planar simple graph, means the requirement for the planarity with E edges and V vertices with number of vertices greater than or equal to 3, then this is the result that E should be less than or equal to 3V minus 6, right? This is the condition that if you have a planar simple graph with E edges and V vertices and minimum number of vertices are greater than or equal to 3, then in that case E will be less than or equal to 3V minus 6. The second corollary is that if G is a connected planar simple graph, then G has a vertex of degree not exceeding 5. Some students get confused with this. What is the statement saying? Listen it carefully. If G is a connected planar simple graph, then G has a vertex of degree not exceeding 5. It means what? That you can't draw a graph with every vertex of degree greater than 5 and planar, right? What does this mean? Let me repeat. Means if you have any connected planar simple graph, then it will have a vertex of degree whose degree will be less than 5. You can't draw, and in case if you want to try, you should certainly give it a try. That try to draw a graph in which every vertex has degree greater than 5, and make sure that the drawing that you are doing is resulting into a connected planar simple graph. I think you won't be able to do, but certainly you should try. And the third corollary is that if a connected planar simple graph has E edges and V vertices with number of vertices greater than or equal to 3 and no circuit of length 3, this is important, then there is another condition that E will be less than or equal to 2V minus 4. Now we are going to look at some problems to understand that how we can apply this result. So let us look at this very important thing, that K5 is non-planar. Suppose we have to show that K5 is non-planar, and I already have shown you that K5 is a non-planar graph by drawing its planar representation, and there we saw that it is not possible to draw K5 without any crossing happening. But I am going to write a mathematical argument for it. So in K5, how many vertices are there? We all know that K5 has 5 vertices. How many edges are there? So K5 has 5 into 4 by 2, n into n minus 1 by 2, that is 10 edges, right? And the result, the corollary 1 says that if G is a connected planar simple graph with E edges and V vertices, and certainly here the example K5, the number of vertices are 5, which is greater than or equal to 3. So this result can be applied. And so what is the result saying? The result is saying that E should be, oh, what is happening? E should be less than or equal to 3V minus 6 as per the requirement of corollary. So what is 3V minus 6 here? 3V minus 6 is 3 into 5 minus 6. So that is equal to 15 minus 6 is equal to 9. How many edges are there? Number of edges are 10. So for this result, suppose I say this is equation 1. For equation 1 to be true, 10 should be less than or equal to 9. It is not possible. Not possible. So it means what? It means K5 is non-planar. Did you get it? Because the corollary says you that if you have a connected planar simple graph with E edges and V vertices, then E should be less than or equal to 3V minus 6. But here we are noticing that 3V minus 6, which is equal to 9, and the number of edges are 10. So this 10 is certainly not less than or equal to 9. So this is not possible. One more thing I want you to understand here, that K5, in K5, why we have applied the corollary 1? Because we know that in K5, this is how it looks like. Just let me quickly draw it so that you don't miss anything. Right. So this is how the K5 looks like, and you can clearly see that K5 has a cycle of length 3, because here the next result says that if there is no circuit of length 3, then we should apply this result. But here we can clearly see that we have a circuit of length 3. Can you see this? Length 1, 2, 3. I repeat it. Let me draw it with another color. That is why we have applied this. That in this graph we do have a circuit of length 3. So that is why we have applied that. Now, if I talk about K33, first of all, you know that K33 does not have a circuit of length 3, right? If I draw it, let me draw. So this is how K33 looks like. 3 here, 3 edges again is joined to this, so 6 edges, and then 3 edges here, 1, 2, and 3, right? So this is K33. Not very good picture, but anyway, You are all smart people, so you may be able to understand. So see, this is K33. So can you find a circuit of length 3? 1, 2, no. 1, 2, no. There is no circuit. No circuit. No circuit of length 3. So it means that here I have to apply the result E should be less than or equal to 2V minus 4. How many edges are there? Number of edges are 3 into 3, 9. Right? K33 will have 3 into 3, 9 edges. How many vertices are there? 3 plus 3, 6. What is 2V minus 4? 2V minus 4 is 2 into 6 minus 4. 12 minus 4 is equal to 8. And here it requires that 9 should be less than or equal to 8. Not possible. Not possible. So we can conclude from this argument or this corollary that K33 is not planar. ठीक है भाई साहब? Okay, let's move. I hope I am not too quick. So I have proved these two results. K5 is not planar. K33 is not planar. I also have drawn the planar representation of K5. There I have shown that crossing is inevitable. It will happen. K33 we have seen that crossing will happen no matter how much you try. And we also have given you the mathematical proof. Now there are few important things which we are going to discuss, and one of them is homeomorphic graph. Let us look at this, what they are saying, that if a graph is planar, so will any graph obtained by removing an edge uv and adding a vertex w together with edge uw and vw. Such an operation is called an elementary subdivision. The graph G1, which I represent by V1, E1, and G2 are called homeomorphic if they can be obtained from the same graph by a sequence of elementary subdivision. So ladies and gentlemen, it is always better to take examples to understand the things. Okay. So suppose I take a graph V1. Let me call this edges like why V1, V2. I mean, let us call ABCD. Yes or no? So A, B, C, D. First of all, let us understand what is elementary subdivision. So the definition of elementary subdivision is that what you do, you have the 4 vertices. So you are going to place one. So you are going to first remove this. So you remove an edge. So I am removing the edge AB and I placed one extra vertex. Let us call it E. And for that, let us join 2 edges. Now this operation, which operation? Removing an edge, putting one extra vertex, and then joining it like this is an elementary subdivision. We can do many elementary subdivision, right? For example, I can remove this edge and I can place one extra vertex, join it, another elementary subdivision. Suppose someone is interested in doing another elementary subdivision. So remove this and place one extra vertex here and join this. This is another elementary subdivision. I can even go further and suppose I want to do some more elementary subdivision. So suppose I remove this edge. Yes. And here I place one extra vertex and join it again. This is another elementary subdivision. So the idea is that when I am saying elementary subdivision, I simply am saying that you remove any of the vertex and join it with 2 new edges, right? So here I can place this vertex, yes, and we are going to join the extra edges. So this process is known as elementary subdivision. Clear or not? And another thing that this result is saying that if you are obtaining, if this graph is a planar graph, then this graph is also a planar graph. So basically the elementary subdivision is not disturbing the planarity of the graph. Okay, ladies and gentlemen. So we just saw that what is elementary subdivision. I hope it is clear. Let us quickly draw one more elementary subdivision. Here we have a graph, simple graph, and I can do one elementary subdivision. I removed this edge, placed one vertex, extra vertex, right, and join these two vertices. Another elementary subdivision of this, I can even remove this edge, right? Like suppose I have this situation. So what we can do, let me remove this edge. Wait a minute. Remove this edge, right? And place one extra vertex over there. And if I place that one extra vertex, I can place it like this and then join. So this is another elementary subdivision, right? And these two graphs which I am obtaining, means this graph and this graph, they are known as homeomorphic graph. So what is elementary subdivision? Remove one edge, place one extra vertex and join it to the other two vertices. The two graphs that we obtain by elementary subdivision are known as homeomorphic graph. And third point, that if I am obtaining a graph through elementary subdivision, what we are noticing that if the original graph is planar, then the homeomorphic graph will also be a planar graph. So based on this concept, there is a very popular result that is known as Kuratowski's theorem. And what is the statement? A graph is non-planar if and only if it contains a subgraph which is homeomorphic to K33 or K5. It is a very powerful result. A graph is non-planar if and only if it contains a subgraph homeomorphic to K33 or K5. To understand this, they have given this a small example. So we have to show that this graph is non-planar. So to show that this graph is non-planar, I want to show you that this graph can be obtained by K5 graph, right? There is a subgraph of this which is nothing but homeomorphic to K5. So this is the vertex A, this is the vertex B, this is the vertex C. Let me call this vertex G and this vertex as I, and let me join these edges. Now what I am going to do, I am going to remove this. Because I am first trying to write the subgraph of it. So I am removing what? I am removing D, I am removing E, and I am removing F, and all the edges which are incident on it, like this part I am removing. So this part is gone. Now I join this, no harm in that. I join this, I join this, right? And what else? I am going to remove this also. So this edge is also removed. And I already have this edge here and this edge here. So if you look at the thing that I have done, I have removed this side, this edge between C and G, and all other vertices and edges. I am also removing the edge between B and C, means this edge, and I am removing this edge. And what is left here is the edge K, vertex K, not edge K, and then this vertex H, and then this vertex J. Yes, legends. So all these vertices are there. And now if I ask you what is this graph, so you can clearly see that here this is 1, 2, 3, 4, 5. If I look at the vertex A, B, C, G and I can consider them as the 5 vertices of K5. And in K5 what I have done, this is a graph. This graph means, if you look at this graph which is a subgraph of, let me call this graph this graph is a subgraph of G. Why it is a subgraph? Because you have removed some edges and vertices, and this subgraph is homeomorphic to what? To K5. Now you will ask me how it is homeomorphic to K5, because this is how the K5 looks like. I'm not drawing it again because it will unnecessarily take time. So let me remove this. I hope you can clearly see that in K5, between this edge, this vertex I and G, you remove this edge and place one extra vertex K and then join. There is an edge in between G and C in K5, so you remove that edge, place one extra vertex and join them. And if same is for this edge between B and C, so you can remove that, and that you can place J and join them. So from K5 you can obtain this graph, and that is why using Kuratowski's theorem we can say that it is a non-planar graph. Yes or no? Because we already know that K5 is non-planar, so certainly a subgraph which I am obtaining and that subgraph is homeomorphic to K5. So the original graph, so G is a non-planar graph. Why G is a non-planar graph? What is the argument? I am saying G is a non-planar graph because G has a subgraph, this graph which is a subgraph of G, and this graph is homeomorphic to K5. So using Kuratowski's theorem we can prove, or we can conclude, that G is a non-planar graph. I hope you have got this. In case if you didn't, please let me know through the comment. Now let us talk about Peterson graph, and this is one of my favorite problem. So using Kuratowski's theorem we are going to show that Peterson graph is non-planar. So first thing we are going to do, we are going to draw that how the Peterson graph can be drawn, because sometimes a student find it confusing to remember. So point number 1, you draw the 5 vertices, right? And then you join these 5 vertices, like you create a cycle or C5 structure, right? So this is your C5 structure. 1, 2, 3, 4, 5, and name them A, B, C, D, E, and then 5 more vertices you place near to each of them. So 1, 2, 3, 4, 5, and you join these edges like this, and then you join this vertex here to the vertex on the other side, so to these 2 vertex, kind of a star structure you will be able to get. Now this vertex and this vertex will be joined, so this is how it will be joined, and this will be joined to this vertex, so another edge here, and this it will be joined to this. Let us name them F, G, H, I and J. If I ask someone that what do you think, does it look like K5 or K33? So most of the time a student answered that it looks like K5. But what I am going to show you that I will be first writing or drawing a subgraph of this graph, and after that I will show you that that subgraph is homeomorphic to K33. So how to draw that subgraph? The first step is that I am going to remove this G. So remove G, the vertex G, and all edges incident on it. So if I do that, let me quickly draw it. So that is A, B, C. Oh, I'm not writing them in the right order, but anyway, you understood the point. So 5 vertices A, B, C, D, and this is how it should be named. So I am first drawing this because I am not disturbing the outer structure, and then this vertex will remain intact, this will remain intact, this will remain intact, this will remain intact. This has been deleted, so this edges will be joined the way it is joined in the original graph, and these 2 edges will also be joined, right? Now this vertex has been removed, so this is, let me first name it A, B, C, D, E, F. G has been removed, so H, I and J. Now since G has been removed, so GI edge has been removed, the GJ edge had been removed. So how many edges it should have? I think JH edge will be present, so this edge I need to join. So now we have 1, 2, 3, 4. It is better to look at the problem this way. Like if you look at this original graph, every vertex is of degree 3. So here A is of degree 3, here E is of degree 3, D is of degree 3, C is of degree 3. But since I have removed G, so 3 of the vertices degree will decrease by 1. So earlier the j degree was 3, now j degree should be 2. So we can clearly see that now j degree is 2. And I degree was 3 earlier, so since this edge has been removed, its degree should be 2. So that degree is 2 here, the degree is 2 here. And b degree should be 2, right? So that I have removed. Now how to redraw, that is my main problem. So let us try to redraw it and be very careful. I already have labeled the degree. So 3, 3, 3, 3, and this degree will be 2. This degree will be 3 and 2 and 2. So we are going to approach this problem in a very smart way. So first we are going to look at K33. So if you remember K33, in K33 there are 6 vertices, right? And each of the vertex is of degree 3. And another property is that every vertex on the one side is joined to all other vertices on the other side. So how can we redraw? Suppose I start with a vertex and the focus should be on all those vertices of degree 3. What I need to do with the vertices of degree 2, that we will also see. So I am first placing the vertex A here, and I am going to put all those vertices on the other side which are adjacent to A and have degree 3. So you see that A is of degree 3, I called it A, and then E is of degree 3, so I am going to place E over here, which is of degree 3. And another vertex of degree 3 is F, so I am going to place F over here, which is of degree 3. If you look at this, A is joined to B, but its degree is 2, so I am going to leave it for that moment. Now come back to the vertex E. E should also have degree 3, and it should be joined to 3 of the vertices of degree 3 here. So E is joined to A, which I already have kind of written here. E is joined to D, right? So D will come on the other side. So let me write D over here, because D is a vertex of degree 3. And E is joined to J, but it's of degree 2, so I leave it for the moment. Now let us come to F. So if you come to F, F is joined to A, already written here, which is of degree 3. F is joined to I, so of degree 2 I am not going to write. But F is joined to H, so I need to write H on the other side because H is of degree 3. And if I talk about H, H is joined to C, and C is of degree 3, so I am going to place C here. So out of 10 vertices, so 1 has been already deleted. Out of remaining 9, I already have plotted the 6. And now start drawing the edges. So there is an edge between A and E, so let us join it. There is an edge between A and F, and so let us join it. And there is an edge between A to B and B to C. So you know what we can do? I can join it like this, and I can place the vertex. Suppose I place the vertex B over here. So you can see that A joined to B and B joined to C. So A joined to B and B joined to C. Okay, so it's okay. Now let us come to E. So E is joined to A, E is joined to D, so I can join E to D. And E should be joined to H, right? But E should be joined to H, but in the process you notice that E is joined to J, which is of degree 2, and then J is joined to H. So I can draw it like this, and I can place J over here. Okay. Now the degree of this vertex A is 3. The degree of this vertex A is 3. Now let us go to other vertices. So let us talk about C now. So C is joined to B, which is of degree 2. C is joined to D, so I am going to join C to D. And C joining to H, so I am going to join C to H. So now it become of degree 3. It's degree 2 now, so certainly there should be an edge between F and H. Do we have an edge between F and H? So F and H, so I am going to join F and H, right? What happened? F and H. Now this H degree become 3. Now D and F. So do we have an edge between D and F? So D is there, F is there, but there is a vertex I coming in between, right? So when I join D and F, so I'm going to join D and F like this, and this I here is coming between D and F because it is of degree 2. So let me put it over here. This is I. Okay, I hope it is clear up to this. So now if you look at this structure, you can clearly see that degree of A is 3, the degree of D is 3, the degree of H is 3, the degree of C is 3, the degree of F is 3, and degree of this E is 3. I have written it twice, so let me remove once, right? And this structure looks like K33. Only thing is that in K33, what I have done, I have removed the edge between A and C, and I placed one vertex B, and then I joined that A to B and B to C. So there is a elementary subdivision here. There is another elementary subdivision between the E and H, because the edge between E and H has been removed and placed, a J vertex has been placed, and then we have joined E to J and J to H. And same is happening with the edge between D and F. I removed the edge and placed one vertex and joined them. So what is this? This is a graph homeomorphic to K33, and this graph is a subgraph of Peterson graph Okay, so what I did, I took the Peterson graph. First I have drawn a subgraph of this Peterson graph. How did I draw the subgraph? I removed the vertex G and all the edges which are incident on G. So this edge I removed, this edge I removed, and this edge I removed. So I got this structure. I have redrawn the structure, and while redrawing the structure, what I have kept in mind, that we know that in K33 these three vertices and these three vertices should be of degree 3. So I tried to place them, and those vertices which are of degree 2, I placed them in the form of that it looks like that they are doing the elementary subdivision. Okay, and when I look at this vertex, it looks like that it is homeomorphic to K33. And as I have shown you earlier, that K33 is a non-planar graph, and using Kuratowski's theorem, because Peterson graph has a subgraph which is homeomorphic to K33, so Peterson graph will be a non-planar graph. So you can write this, that Peterson graph is a non-planar graph. I have tried to explain it in very easy way, and I was very slow also, but still I would suggest you that try it yourself once and find out that whether you have understood it or not. Okay, this is a very important result. Now let us move to the final thing, that what is crossing number and thickness of a graph. So what do we mean by crossing number? The crossing number of a simple graph is the minimum number of crossing that can occur when this graph is drawn in the plane where no three arcs representing edges are permitted to cross at the same point. So we have seen our earlier example that when we have drawn K33 during its planar representation, I was not able to draw without at least one crossing happening. So let us quickly see it again. Here I have joined it. This I can join, this I can join, right? Now this edge and this edge I can join. This vertex, not edge, sorry, ignore that. And this vertex and this vertex can also be joined. So now the degree of this vertex is 3, the degree of this vertex is 3, the degree of this vertex is 3. The degree of this vertex is 2 and 2. So I need to join this to this vertex. So first I joined it to this vertex. So now its degree became 3. And I also need to join this vertex to, so degree 3, degree 3, degree 3, degree 3. Now these two should be joined because their degree is 1. So if I have to join them, you can see that no matter how you try, if you want to join them, one crossing will certainly happen, right? If you join this, so there is a crossing happening at this point, right? So the minimum number of crossing happening is 1, so the crossing number of K33 is equal to 1. Okay. Similarly, if you talk about K5, we have seen earlier also, but let us quickly draw it in this context, that what is the crossing number of K5. So this is how the K5 should be drawn. First you draw this, then you draw this, then you have to draw this edge. So now degree of this becomes 4. Degree of this is 3, so I need to join this and this. So without crossing I can join them. Now this degree becomes 4. Now this degree is 1, 2, 3, and this degree is 3. So what we can do, we can join this edge at this vertex and this vertex. So now this degree becomes 4 also. So now the degree of this vertex is 1, 2, 3, and degree of this vertex is 1, 2, 3. So I have to join them, right? So if I join them, no matter how we try, if I move in this direction, the crossing will happen. If we move in this direction, a crossing will happen, because I just have to join this. Means there is no other way without avoiding the crossing. So if I draw this, this crossing is happening, and here one crossing is happening. So the crossing number is 1, right? So crossing number of K5 is equal to 1. So I hope through these two examples you have understood that what is the crossing number. And here it is important to note that it is the minimum number of crossings. So don't draw it in such a way that multiple crossing happening, even though it could have been avoided. Now what is the thickness of the graph? Thickness of a simple graph G is the smallest number of planar subgraph of G that have G as their union, right? So it is very clear that suppose I take this example of K5, and in K5 if I draw this two subgraph of K5, like this is how it is being drawn. So suppose I join them like this. Okay, so here I can, this degree I have to make 4, so let us join it, right? So degree of this and this, so I can join this. So now this degree become 4, because I want to draw two subgraphs so that the crossing can be avoided. And now this degree is 3 and this degree is 3, so I can draw this. Its degree became 4, its degree became 4, so now 4, 4. Now for this two I can draw another subgraph of this. So let me call this vertex A, B, C, D and E. And here we have A, B, C, D and E. And now I am drawing a subgraph like B and D. Okay, and if I take the union of it, I will get the K5, because all the edges have been drawn. You can see that how many edges are there: 1 edge, 2 edge, 3 edge, 4 edge, 5 edge, 6, 7, 8 and 9. So 9 edges are already drawn. In K10 there are 10 edges, and because this edge was resulting into the crossing, so I can draw it as two different smaller graphs or two different subgraphs, and if I take their union, this graph union this graph, I will get K5. So minimum number of two subgraphs are needed. So what is the thickness? The thickness of a simple graph is the smallest number of planar subgraph of G that have G as their union. So you can clearly see that these two are the planar subgraph. So what is the thickness of K5? The thickness of K5 is 2. So I think you have understood about what is crossing number and thickness. I am putting a lot of effort to create these videos, and I would sincerely request you that if you are enjoying the video and learning the new concept and things, then you should like the video, and not only like, you should share with everyone who is taking this course and looking for better quality content, right? So this is all about this video. I hope you enjoyed it. Thanks for watching.